Oh, has anybody been able to get in the computer site? Okay. Yeah. Yeah, they're both. Anybody able to get the videos under there? Okay, I've been downloading the videos, so you should be able to find a link on there that you want to review the lectures. Okay, well, let's go ahead and get back in this stuff. Okay, last time we looked at acetals and ketals. Okay. Today we want to look at the mechanism of how these things form. Okay? So it's a long mechanism, but if you remember the mechanism we did with water adding on last time, this one shouldn't be a problem at all. Okay? So let's choose an aldehyde or a ketone. Let's maybe choose this ketone here. Okay. And let's react it with an alcohol and an acid catalyst. Okay. So this is the setup that we want to look at here. Okay. So again, remember the carbonyl has two lone pairs. What's the first thing that oxygen's going to attack?
The H plus.
Okay, the H plus, the proton. So let's go ahead and add that on. Okay, this is always the first step, protonation. Okay, remember what protonation did. Okay, it added on to the oxygen, make it a positive charge, which did what to the carbonyl? It made it what? More reactive by making that carbon what? More electrophilic, because that oxygen is now what? More electronegative. Okay? So we covered that last time. I hope you digested that by now. Okay? So the second step will now bring in the nucleophile. Where will that nucleophile want to attack? The carbon on the carbonyl. So it attacks there, and then what happens? The high electrons move up to the oxygen. Okay. So the carbonyl has now turned into an OH, and we've added on this alcohol here to what was the carbonyl. Okay. So this is just like water having added on. Remember the property of this hydrogen here? It's acidic because this oxygen's now very electronegative. So let's remove the acidic hydrogen. And remember, we remove it with base. And so, as a result, have this thing. Does anybody remember the name for that? That's right, we're halfway there. So we're the hemi from the ketone, we're the hemiketone. And this is really where we ended up with the water reaction. That's where we stopped. But with this one, we keep going on. Okay? So what we'll do now is another protonation. Okay? Where do you think that proton will go? You got two oxygens to choose from. You got lone pair here and over here. Which one do you think will attack? Okay. Well, the answer is they both do. If this one attacks, what do? We go back to this structure. We go backwards. We don't want to go backwards. We want to go forwards. So we'll choose this one here. Okay, so we protonated the alcohol. When we do that, what molecule do we create here? Water, which is what a good leaving group. Okay, let's go ahead and circle water. That thing wants to leave, so let's go ahead and make it leave. So when it leaves, we get a carbocation at that point. Okay. What's special about that carbocation? What can we draw? We can draw what? A resonance structure. Okay? We can draw a resonance structure. So let's draw a resonance structure. I hear rappers going on. Nobody's eating. Okay. So here we see two driving forces for this step here to occur. What are they? We already know. One, we have water, which is a good leaving group. So that would like to leave. Secondly, what we form is a carbocation that is resonance stabilized. So a second factor to cause that. Okay? Well, lastly, what we do is we bring in our second nucleophile, okay? And let's just have it attack this carbocation over here, okay? It could attack the carbonyl and push those up to give you the same thing. Let's just attack that one to make it easier. Okay. So here the second alcohol is added on. And if you note on this one, we have a hydrogen on oxygen with a positive charge. So this hydrogen is now what? Acidic, just like that one was. So we can remove it with base. And get our final product. Which here is the ketone.
I have a question.
Question?
I understand where the oxygen from our base attacked on the carbocation, but what happened to the lone pair that came down from the oxygen on our first resonance structure? Yeah, the lone pair is coming down.
Well, that was forming this resonance here.
Oh, that's what you were showing?
Yeah.
Okay.
So just leave it alone.
Okay.
Yeah.
Could we have used water instead of methanol
On this step here,
on that one and the one before?
on this step here, you could use water or methanol to remove the acidic hydrogen. Okay, but not here. Here I need to use my second alcohol because I'm trying to form the ketone. If I would have used water, I would have reformed this thing here.
Okay, and the step before the human ketone, we use water to remove that instead of oxygen.
That's right, that's right. If I just use the alcohol all the way through, just to keep it consistent and keep it easy to remember. Okay. Any other questions on that? Okay. All right, so this is the mechanism that you will need to do, okay? Let's go through it again so that you can see, you won't have to memorize the whole thing, but just be able to see what goes on in each step. And then you'll be able to get to the end that way. So at the beginning, we protonate the carbonyl, more electrophilic carbon, nucleophile attacks, that makes sense. So I add it on. Okay, once I see this, I see my acidic hydrogen, so let's remove that. And now I'm at the hemi ketone. Then I take the OH, protonate, to make water, which is a good leaving group, to form a resonance stabilized carbocation. Okay. The second alcohol adds on, and that gets deprotonated to finally give you the ketone. Okay. Do that.
That's good.
Still good? Okay. So make sure you have that down. Crucial mechanism. Okay, so what's the importance if you look at your outline? Okay, we're on number 7 there. Let's go down to number 8 and look at what's the importance of making acetals and ketones. Okay, so let's draw these two molecules. Okay, there was the starting material, the cyclohexanone. And let's compare that with the final product we made. Which is this here. Okay. If you compare these two, this one here is reactive with nucleophiles. Okay, the carbonyl can react with a nucleophile. But when you make the ketal functional group, I've now taken away that reactivity. So this will no longer react with nucleophiles. Okay. Now the key thing about these two is that these are interconvertible. I can take my ketal, we won't look at the mechanism, but I can transform it back to the ketone using H3O plus and heat. Okay, and that combination is what's called hydrolysis. Okay. So in other words, what's the purpose of showing that? The purpose is that this ketal group is what? A hidden carbonyl, isn't it? Because I can convert it back. So what I can do is transform it to a ketal. Now this will no longer react with a nucleophile. So if I have another part of the molecule that I do want to react with a nucleophile, it can do that. After I'm done with that reaction, I can then come back and transform that back to the carbonyl using hydrolysis. Okay? So that's the utility of making acetals and ketals. It's a protection group. Okay? And then I can transform back at any time that I want to. Okay? So that takes care of topics 7 and 8. Okay? We did topic 9, which was the Wittig reaction. Okay? Let's go on to topic 10. Okay, topic 10. We're going to react our aldehyde or ketone with HCN, KCN. Let's see how this setup works. When you see HCN, what do you think that's going to act as? What's that going to act as? What's it look like? Yeah, you've seen, looks like HCl in a way. Okay. So this thing will act as an acid. So it's simply going to give its hydrogen to the oxygen. So again, we have activated our carbonyl by protonating it. KCN is a salt that can then split up into its ions. And when it does, the CN minus is what's going to act as our nucleophile in this case. So in the next step, the cyanoion or cyanide ion is going to come in. Where is it going to react with? The carbonyl, just like our alcohols and waters did and Grignards. Okay, so now that can attack the carbonyl carbon and transform the carbonyl into what? An OH. And so now we have these two groups on the same carbon, a cyanide group and the OH group. And this is what's called a cyanohydrin. Okay? A cyanohydrin. Cyano from the CN and hydrin from the OH. Okay? So, very simple reaction. Suppose I gave that molecule to you. See if you can draw the product for this reaction. So again, where's the chemistry going to occur? At the carbonyl. This is the only part of the molecule I have to look at. All this other stuff is just luggage. So anytime I see this combination, it's going to convert the carbonyl what? To what? An OH and a CN. It's that simple. Question?
On an example, you just want us to write the product, or we have to do the whole mechanism?
Well, if I just ask for the product, then if I ask for the mechanism, then, so I'll specify. Any other questions? Okay, so that's the end of these different nucleophiles, okay? We're next going to go to number 11 and 12 on the sheet. Okay? And look at something a little bit different. How do you think you would pronounce that word? Okay? Students always get it wrong. It's imine, not I mean. Imine. Imine. Okay? So we're going to look at imine formations. Okay? Here what we're going to do is get a look at an imine. Okay. This is what an imine is. It's a carbon double bonded to a nitrogen. And this nitrogen can have something over here. Okay. This is what we're going to get into now. And specifically, we're going to look at how a carbonyl can transform into an imine. Okay. So, some strange chemistry going on. So what kind of setup are we going to look at to do that? Okay. What we're going to do is take an aldehyde or a ketone plus a molecule like this. What kind of molecule do you think that is? Okay, those are amines. Okay, so we're going to take some kind of aldehyde or ketone and react it with an amine. And the result of that will be that. So, imines come from amines and carbonyl compound. Okay? Do you see what I mean? Okay. All right. So let's look at some examples of this stuff. Here's one example. Note that these reactions use an acid catalyst. Okay. So here you have an alkyl group on the nitrogen to give you this kind of imine. Okay, this kind of imine what's called a shift base. Okay? Another kind of imine if you reacted that and H plus, is that kind of compound. That's called an oxime. Or we could bring in this kind of amine, where we have two NH2s bonded together. Give us that kind of molecule, which is called a hydrazone. Okay. So write down, these are different examples of imines, okay? Where what's the only difference? What this R is, okay? Any questions on those? Okay. So make sure you can identify the particular functional group with its name, okay? Got some new names here. All right? So, question?
Would these be the only three options, or would you have more? If we had different arguments attached, would we have to do the names?
Right, these are the three I'll hold you to. Okay. There are some others, but these are the three main ones. Okay, so if you have an alkyl group, shift base, an OH, oxime, NH2, hydrazone. That's plenty for us. Okay. Any other questions on that? Okay. Let's look at some examples of this. Again, we'll do the mechanism next time. But now what I want you to do is take these examples I'm going to give you, okay, and see if you can work backwards a little bit. You can take these two examples and draw what the original molecules were to make those. Okay? I'll give you a minute or two. Okay. Maybe start with the bottom one first. That's the easier one. this one here. You want to come up and show off your answer? Okay, very good. You got it right. Anybody else get it right? Okay, that was the easy one. Okay, so what you do is basically come to the double bond, split it in two. One side becomes the carbonyl, the other side becomes the nitrogen, and whatever it has. Note that you had to add on 2 hydrogens here. Okay? So with that one in mind, as some help, now see if you can draw the molecules involved in that one. Okay? Note too, you needed a H+. See if you can draw where that came from. Did you get it? Now, all the answers I'm seeing so far is what the other class drew, drawing illegal structures. That's what they drew too. Anybody get it? Nobody got it in last class.
Like, give me a second. I think I'm on something or not.
Anybody get it? Anybody want to come to the board? About you, Quincy. Did you get it?
I don't think so. Want me to try?
Okay, I want confidence up here. Anybody got any confidence? Lawful.
Might as well do it yourself.
It is wrong.
All right, what about you, George? No?
Okay.
So, come to the double bond. Are you confident? Only if you're confident, George. No. I didn't want the camera to see that. Okay, but that was the answer I've been seeing as I walked around the class. Okay, so you split this thing in two. All right, so let's draw it here. Okay, so you split those two atoms in two. Okay, and what do? The nitrogen gets 2 hydrogens, so let's give it 2 hydrogens here. And the carbon gets what? The carbonyl. See how simple that was? Okay? If you just followed the rules that you did here, you could have got that one. Okay? But don't feel bad if you didn't get it. But now, you should be able to get it.
Okay, can you put it up there again Wednesday, ask somebody to come up to the board?
Split it. One side gets carbonyl, other side gets 2 hydrogen. All right, so let's stop there for today. Again, your homework is downstairs. You want to pick it up.